Scientists recently pointed the James Webb Space Telescope at Saturn's largest moon and found clouds sitting in a location the seasonal models said should be empty. That single observation, made in November of 2022, has spent the past few years quietly forcing planetary scientists to revise how they think about Titan's atmosphere. It has not made many headlines, because it is not the kind of finding that fits neatly into a press release. It is a discrepancy, and discrepancies take years to explain properly. This video walks through what Webb actually measured at Titan, why those measurements do not match the picture built during the Cassini mission, and why a nuclear-powered helicopter currently being assembled at Johns Hopkins is going to fly through whatever. The real answer turns out to be Titan is the largest moon of Saturn and the second largest moon in the solar system after Jupiter's Ganymede. It is larger than the planet Mercury, though less massive, because much of its bulk is water ice rather than rock. What makes Titan unusual among moons is not its size. It is the atmosphere. Titan is the only moon in the solar system with a substantial atmosphere, thick enough that the surface pressure is about 1.5 times what you would feel standing at sea level on Earth. That atmosphere is roughly 95% nitrogen, similar in that respect to Earth's own air, with about 5% methane and small amounts of other hydrocarbons produced when sunlight breaks methane molecules apart. That combination, nitrogen and methane under real atmospheric pressure, is what allows something no other body in the solar system has: weather made of a substance other than water. On Titan, methane and its close chemical relative ethane behave the way water does on Earth. They evaporate into the atmosphere, condense into clouds, fall as rain, and pool into lakes and seas on the surface. Titan has a hydrological cycle. It is simply not a water cycle. It is a hydrocarbon cycle, running at a surface temperature of about 94 Kelvin, or minus 179 degrees Celsius, cold enough that water ice on Titan behaves the way solid rock does on Earth, and liquid methane takes water's place as the working fluid of the weather system. Our understanding of that hydrocarbon cycle comes almost entirely from one mission. The Cassini spacecraft arrived at Saturn in 2004, carrying with it the European Huygens probe, which separated from Cassini and descended through Titan's atmosphere in January of 2005. Huygens is still the only spacecraft ever to land on a world in the outer solar system. It transmitted data from the surface for a little over an hour and a half before its batteries ran out, capturing images of a landscape shaped by liquid flow, drainage channels, and rounded pebbles that looked remarkably like a dry riverbed on Earth, except made of water, ice cobbles, sitting in a landscape carved by liquid methane rather than liquid water. Cassini itself continued flying past Titan for another 12 years, using radar to map the surface through the moon's permanent orange haze. Since Titan's atmosphere is opaque to visible light in a way that makes ordinary cameras nearly useless for seeing the ground, those radar passes mapped hydrocarbon lakes and seas concentrated near Titan's North Pole, the largest of them named Kraken Mare, roughly the size of the Caspian Sea on Earth. Cassini flew past Titan more than 100 times before the mission ended in September of 2017, when the spacecraft was deliberately steered into Saturn's atmosphere to burn up, a decision made specifically to prevent any chance of contaminating Titan or the icy moon Enceladus with microbes from Earth-13. Years of data and more than 100 close passes. Sounds like an enormous amount of information, and it is. But it is worth being precise about what that data actually covered. Cassini's cameras and radar mapped fractions of Titan's surface across roughly 1/3 of a single Titan year, since one full orbit of Saturn, and therefore one full Titan year, takes about 29.5 Earth years. A single Titan season lasts around 7.5 Earth years. Cassini caught a portion of that cycle, not the whole thing, and much of what scientists concluded about Titan's climate came from extrapolating those partial observations, forward and backward in time using atmospheric models built from the available data. Those models were already showing cracks before Cassini's mission ended. Late in the mission, Cassini's radar detected strange, bright features in Ligeia Mare, one of Titan's northern seas, that appeared, disappeared, and reappeared in different shapes across repeated passes. Scientists nicknamed them Magic Islands. The leading explanations include waves on the liquid surface, bubbles of nitrogen gas coming out of solution as the liquid warmed slightly, or floating solid material, but no explanation has been confirmed. Cassini also recorded seasonal cloud patterns that drifted from what the atmospheric models predicted, and observed the upper atmosphere responding to solar activity in ways researchers were still debating when the spacecraft was retired. The foundation Cassini built was real and valuable. It was also, by the mission's own data, incomplete in specific and measurable ways. For roughly 5 years after Cassini's mission ended, Titan was studied almost entirely through ground-based telescopes and archived data, since no dedicated spacecraft was in position to observe it directly. The atmospheric models built during and just after the Cassini era stayed largely fixed during that gap, and design work on the next Titan mission moved forward using that frozen picture as its baseline. Then, in November of 2022, the James Webb Space Telescope turned its instruments towards Saturn and began a new observing campaign of Titan. Using tools Cassini never carried, Webb is not a replacement for an orbiter or a lander. It cannot map the surface at Cassini's resolution, and it cannot sample the atmosphere directly the way Huygens did during its descent. What Webb brings instead is spectroscopy, the ability to break incoming light into its component wavelengths and identify specific molecules by the exact pattern of light they absorb or emit. Using its near-infrared camera, known as NIRCam, and its near-infrared spectrograph, NIRSpec, Webb can measure the chemical composition and temperature structure of Titan's atmosphere with a precision Cassini's cameras and radar were never designed to achieve. The first results came quickly. During the November 2022 observing run, Webb detected bright clouds in Titan's troposphere, the lowest layer of the atmosphere positioned over and near Kraken Mare, that large northern sea mapped by Cassini's radar. The problem was timing. Titan's seasons move slowly, and the atmospheric models built from Cassini-era data predicted that clouds at that latitude, at that point in Titan's slow seasonal cycle, should have been rare or largely absent. Webb found active cloud cover exactly where the models said there should be comparatively little. A second observing campaign in July of 2023 confirmed that the tropospheric weather activity was not a one-time anomaly. It was a pattern. Webb's instruments also measured Titan's stratospheric haze, the thick layer of aerosol particles sitting high above the surface that gives Titan its characteristic orange color and makes the ground impossible to see clearly in visible light. The haze Webb measured came back brighter and physically thicker than the baseline established from Cassini's observations. A thicker haze layer means more particles suspended in the upper atmosphere, which in turn means the underlying chemistry that produces those particles is running at a higher rate than the existing models accounted for. The most significant single result from Webb's Titan campaign was the detection of a molecule called the methyl radical, written chemically as CH3. To understand why that detection matters, it helps to walk through the chemistry it comes from. Titan's atmosphere is roughly 5% methane, and methane is a fragile molecule when exposed to ultraviolet sunlight. Even though Titan receives only about 1% of the sunlight that reaches Earth, because Saturn orbits so much farther from the Sun, that small amount of ultraviolet radiation is still enough to break methane molecules apart in the upper atmosphere. When a methane molecule absorbs a high-energy photon, it can lose a hydrogen atom, leaving behind the methyl radical, a fragment with 1 carbon atom and 3 hydrogen atoms instead of methane's 4. The methyl radical is extremely reactive and extremely short-lived. It does not persist. Within a fraction of a second of forming, it collides with another molecule and reacts further, eventually building up into heavier hydrocarbons like ethane and acetylene, which are the raw materials of Titan's haze layer. Because CH3 exists for such a brief window, directly observing it requires catching the chemistry in the act, rather than measuring the more stable end products it eventually becomes. Before Webb, that direct detection had never been achieved at Titan. Webb's spectrograph measured it directly, in 2023, at abundances and altitudes that required scientists to revise the photochemical models used to describe how Titan's haze is produced. Here is why that revision matters beyond the immediate chemistry. The rate at which methane breaks down and recombines into haze particles determines how quickly and how thickly that haze accumulates in the atmosphere. If the photochemistry is running faster than previously modeled, which is what the CH3 measurement and the brighter haze readings both indicate, then the haze is not just present, it is being actively replenished at a higher rate than earlier calculations assumed. A denser, more actively produced haze layer has a direct consequence for any future mission trying to see through Titan's atmosphere from orbit or from the air, because it changes how much light penetrates down to the surface and how much visibility any camera or sensor will actually have once it arrives. There is a second and arguably deeper puzzle sitting underneath all of this. Methane in Titan's atmosphere is not a stable, permanent feature. The same ultraviolet breakdown process that produces the methyl radical is slowly destroying methane throughout the atmosphere, and it is doing so continuously. Based on the rate of that breakdown, researchers estimate that all of the methane currently in Titan's atmosphere should be consumed within roughly 30 million years, which is a short span in geological terms. 30 million years ago on Earth, mammals were already diversifying after the extinction of the dinosaurs. On the scale of Titan's 4.5 billion year history, 30 million years is close to nothing. Yet Titan's atmosphere still contains methane today, at roughly the same 5% concentration scientists have measured across multiple missions. That means something is replenishing the methane supply continuously on a timescale far shorter than the age of the moon itself. Nobody has confirmed what that source is. The leading candidates include cryovolcanism, icy analogues to volcanic eruptions that could vent methane trapped beneath the surface, slow ongoing outgassing through cracks or porous ice, or a subsurface reservoir, possibly connected to the ocean of liquid water that models suggest exists beneath Titan's ice shell. Each of these explanations implies that Titan is more geologically active in its interior than direct observations have confirmed. Webb's data did not resolve this question. It sharpened it by confirming that the methane destruction process runs quickly enough that the replenishment mystery cannot be dismissed as a rounding error in an old model. It helps at this point to step back and lay out Titan's physical environment in full, because the numbers involved make it easy to misjudge just how different this world is from Earth, despite the surface-level similarities of clouds, rain, rivers, lakes, and seas. Titan orbits Saturn once every 15.5 Earth days, but the number that matters for climate is Saturn's orbit around the Sun, which takes about 29.5 Earth years. That is Titan's year. A single season, 1/4 of that cycle, lasts roughly 7.5 Earth years. A Titan summer is not a few warm months. It is nearly a decade of one slowly changing configuration of sunlight, moving so gradually that an atmospheric feature which builds up over one season may still be dissipating when the next season begins. Surface gravity on Titan is about 14% of Earth's, close to 1/7. Surface atmospheric pressure is about 145% of Earth's, meaning the air pressing down on the surface is denser and heavier relative to gravity than almost anywhere else humans have sent a spacecraft. Sunlight reaching Titan's surface is only about 1% of what reaches Earth, because of the combination of distance from the Sun and the thick, hazy atmosphere scattering and absorbing much of what does arrive. Standing on Titan at local noon, the ambient light would resemble deep twilight on Earth, dim enough that reading without an additional light source would be difficult. Combine those four numbers: low gravity, high pressure, low sunlight, and cold temperature, and Titan stops looking like a variant of Earth's climate and starts looking like a genuinely different physical regime. Low gravity combined with high atmospheric density changes how particles and liquid droplets behave in the air. A raindrop of liquid methane on Titan can grow larger than a raindrop of water ever could on Earth, in some estimates reaching a size closer to a small grape, because the dense atmosphere and weak gravity both work against the droplet breaking apart or falling quickly. That same methane raindrop also falls more slowly, drifting down at something closer to a gentle descent than an Earth rainstorm's downpour. The dense atmosphere has other consequences. Because the air is so much denser than Earth's relative to the force needed to move it, a comparatively modest wind on Titan carries far more physical momentum than the same wind speed would on Earth. That extra carrying power is visible on the surface in the form of massive dune fields, mapped by Cassini's radar across a large fraction of Titan's equatorial regions, running hundreds of kilometers in length. These are not sand dunes in the terrestrial sense. They are built from solid hydrocarbon grains, organic particles that settled out of the atmosphere over long periods, shaped into dune formations by winds operating under physical rules. No aircraft engineer on Earth has ever had to design against directly. Titan is often described, accurately, as the most habitable moon in the outer solar system, in the specific sense that its combination of a thick atmosphere, complex organic chemistry, and a possible subsurface liquid water ocean makes it one of the more scientifically interesting targets in the search for the conditions that could support life, or at least the chemistry that might precede it. That description is a comparison, not a conclusion. Titan is being ranked against Europa's ice-covered ocean, Enceladus's smaller icy shell, and Io's radiation-soaked volcanic surface, all of which are far more hostile to any mission by nearly every practical measure. Being the least difficult member of that group does not mean Titan is friendly. Its surface temperature of -179 degrees Celsius is cold enough to make many ordinary engineering materials behave in unexpected ways. Standard battery chemistries lose most of their capacity. Metals that are ductile at room temperature become brittle enough to fracture like glass under stress. Rubber seals stiffen and lose the flexibility needed to hold a pressurized seal. Every material choice for a Titan mission has to be tested and often redesigned specifically for that thermal environment. This is the environment that NASA's Dragonfly mission is being built to fly through. Dragonfly is a funded, active NASA mission, not a concept study, currently in fabrication at the Johns Hopkins Applied Physics Laboratory, with a launch scheduled for July of 2028 and an arrival at Titan planned for 2034. Its projected cost is roughly $3,350 million, a figure that grew substantially from earlier estimates closer to $1 billion as the mission's design matured. Dragonfly is built as an octocopter, a rotorcraft with 8 rotors, designed to make short flights of several kilometers at a time, hopping between sites on Titan's surface to sample and analyze the chemistry at each location. Because Titan receives only about 1% of the sunlight Earth does, solar power is not a workable option for an aircraft that needs to operate reliably across Titan's long seasons and low light levels. Dragonfly instead carries a multi-mission radioisotope thermoelectric generator, the same type of nuclear power source that has powered the Curiosity and Perseverance rovers on Mars, converting the heat released by the natural decay of radioactive material into a steady supply of electricity regardless of sunlight availability. That choice was less a preference than a requirement given Titan's light environment. Dragonfly's primary science target is the Selk impact crater, a site scientists believe may preserve evidence of past interaction between liquid water, delivered briefly by the impact that formed the crater, and the organic material that makes up much of Titan's surface chemistry. That kind of interaction, liquid water mixing with complex carbon-based molecules, even briefly, is exactly the kind of environment relevant to questions about the chemical steps that can lead toward the building blocks of life. Sampling that site is one of the primary reasons Dragonfly was selected for development in the first place. Every hour of Dragonfly's planned flight profile, how high it flies, how far each hop travels, how the rotors are sized, how the navigation cameras are expected to perform, was calculated using atmospheric models built from Cassini-era data and the modeling work done in the years immediately following. Those models describe wind speeds at different altitudes, haze density and how it affects visibility, and temperature profiles through the atmosphere that the rotorcraft has to fly through safely. Webb's more recent findings, a thicker and more actively produced haze layer, tropospheric weather occurring in places and at times the seasonal models did not predict, and photochemistry running faster than assumed, are arriving during the final stages of Dragonfly's design and fabrication, a phase in which major structural changes to the spacecraft are effectively no longer possible. This is not a criticism of how Dragonfly was designed. Missions to the outer solar system take years to plan and years more to build, and engineers have no choice but to work from the best available data at the time decisions are locked in. It is simply a description of a real timing problem. The atmospheric picture Dragonfly was engineered against is being revised while the spacecraft is being assembled, and the revisions matter specifically because Dragonfly depends on cameras for navigation and landing site selection, meaning its ability to see clearly through Titan's atmosphere is directly tied to how thick that haze actually turns out to be when the spacecraft arrives in 2034. There is also the matter of distance and communication delay, which shapes how Dragonfly has to operate regardless of what the atmosphere does. Titan sits between roughly 1,200,000,000 and 1,500,000,000 kilometers from Earth depending on the relative positions of the two planets, and radio signals traveling at the speed of light take between about 68 and 84 minutes to make that one-way trip. A round-trip communication, a command sent from Earth and a confirmation received back, takes close to 3 hours. That delay makes real-time piloting from Earth physically impossible. Every flight Dragonfly makes has to be executed autonomously. using onboard systems to evaluate terrain and hazards in the moments before and during each hop, because there is no way for a human operator to react in time to prevent a problem as it happens. It is worth comparing Dragonfly to Ingenuity, the small helicopter that operated on Mars alongside the Perseverance rover, since both are often mentioned in the same breath as pioneering examples of powered flight beyond Earth. The comparison actually highlights how much more difficult Dragonfly's operating environment is. Mars has an atmosphere with less than 1% of Earth's density at the surface, thin enough that Ingenuity's rotors had to spin extremely fast just to generate enough lift. But that thin atmosphere also meant Ingenuity operated with a fairly good understanding of the air it was flying through. Close daylight communication with Earth measured in minutes rather than hours, and near real-time monitoring by its engineering team. Dragonfly flies in the opposite kind of atmosphere, dense rather than thin under gravity, about 1/7 of Earth's rather than roughly 1/3 as on Mars, in near constant twilight rather than the comparatively bright daylight Mars receives, across a communication delay measured in tens of minutes each way rather than a few minutes, and using atmospheric models that recent data suggests may be measurably out of date. Every one of those differences adds difficulty rather than removing it. Ingenuity was a technology demonstration that succeeded well beyond its planned lifetime. Dragonfly is a full science mission with a specific, difficult target, flying blind to the most recent atmospheric data by the nature of how long spacecraft design cycles take. Missions to Titan are rare events on a human timescale. The travel time alone, using current propulsion technology, runs between about 6 and 7 years. And building and funding a mission of Dragonfly's scale and cost is not something NASA or any other space agency does routinely. If a failure occurs at the destination, there is no quick follow-up mission waiting to try again. A serious problem during Dragonfly's descent, landing, or early flights would likely mean the end of any dedicated Titan surface exploration for a generation or more, simply because of how long it takes to plan, fund, and build a mission capable of replacing it. None of this means Dragonfly is likely to fail. It means the margin for error is unusually small, and that margin is precisely why the gap between Webb's newer atmospheric data and the older models Dragonfly was designed against matters as much as it does. It is also worth being clear about how information moves from a mission like Webb into public understanding, because that process shapes how most people encounter findings like these. NASA's public communications about the Titan observations use accurate but carefully chosen language, describing the results as an unprecedented view and confirmation of atmospheric activity. Every one of those statements is true. The underlying scientific papers, written for other researchers rather than the general public, go further, describing specific departures from the seasonal behavior the older models predicted and discussing what the methyl radical detection means for revising the photochemical models. Both the press release and the paper are honest documents. They are simply written for different audiences and different purposes. A press release exists partly to communicate results and partly to support an agency's ongoing case for funding, particularly during periods of tight federal budgets and competition between large flagship missions for limited resources. A specific statement acknowledging that new data is complicating a multi-billion-dollar mission's design assumptions is the kind of sentence that invites difficult questions in a budget hearing. So the language that reaches the public tends to emphasize the achievement of the observation itself, rather than the complications it introduces for other programs. This is not evidence of dishonesty. It is a normal and well-understood feature of how large scientific institutions communicate, visible across virtually every space agency and research organization, and NASA generally handles this balancing act reasonably well by international standards. But it does mean that the more complicated implications of a finding like this one tend to reach public awareness later, and through fewer channels, than the initial announcement does. Titan is not an isolated case of a world turning out to be more complicated than expected once a better instrument arrives. It fits a broader pattern, visible across nearly every body in the outer solar system, that has been examined closely more than once. Europa, one of Jupiter's large moons, was initially thought to have a relatively thin ice shell covering its subsurface ocean, based on earlier modeling and limited observations. Later data, drawn from a combination of Galileo spacecraft measurements and subsequent analysis, suggested the ice shell is considerably thicker and that the moon is more geologically active than the earlier picture allowed. with evidence of plumes and surface features consistent with ongoing internal activity. Enceladus, a much smaller icy moon of Saturn, was expected before Cassini's arrival to be a quiet, largely inactive world, too small to retain significant internal heat. Cassini instead discovered massive plumes of water vapor and ice particles erupting from cracks near its south pole, venting material from a subsurface ocean that essentially nobody had confidently predicted before the mission observed it directly. That single discovery reshaped Enceladus from an afterthought in Saturn's system into one of the leading targets in the search for potentially habitable environments beyond Earth. Pluto offers a similarly striking example. Before NASA's New Horizons spacecraft flew past it in 2015, Pluto was widely assumed to be an old, heavily cratered, geologically dead world, having had billions of years to cool and settle into inactivity. New Horizons instead found regions of strikingly young crater-free surface, along with evidence suggestive of ongoing or relatively recent geological activity, on a body that should have run out of internal heat long before humans existed. Io, Jupiter's innermost large moon, was already known to be volcanically active before more detailed observation, but successive missions have repeatedly revised the estimated scale of that activity upward, finding it to be more intense and more frequent than earlier models suggested. Titan fits directly into this pattern rather than standing apart from it. In each of these cases, an outer solar system body that scientists believed they understood reasonably well, based on the best available data at the time, turned out on closer or repeated inspection to be more active, more chemically complex or more dynamic than the existing models predicted. That is not a criticism of the scientists who built those earlier models. It reflects a real and consistent bias built into how planetary models get made in the first place. Most of the physical assumptions used to model these distant worlds were originally calibrated using data from Earth and the Moon, the two bodies humans understand best, and then extended outward to very different environments using best available extrapolations. Titan's atmosphere, Europa's ice shell, Enceladus's interior, and Io's volcanism all operate under physical conditions different enough from Earth and the Moon that assumptions calibrated close to home do not transfer cleanly. This pattern has consequences that reach well beyond the outer solar system. The James Webb Space Telescope is currently being used to measure the atmospheres of planets orbiting other stars, identifying the chemical composition of exoplanet atmospheres based on how starlight filters through them during a transit. Those exoplanet analyses depend on atmospheric models built using the same general class of physics and chemistry used to model Titan's atmosphere before Webb's more recent observations required revisions. If Titan, a world humans have orbited for 13 years and physically landed a probe on, still produced atmospheric surprises significant enough to affect an active multi-billion-dollar mission's design, that raises a reasonable question about how much confidence is warranted in atmospheric models applied to exoplanets that have only ever been observed as a fraction of a single pixel of light. With none of the direct, close-range verification Titan has received, it is worth being precise about what remains genuinely unresolved after Webb's observations, since the goal here is not to manufacture mystery where the science is actually settled. The source of Titan's replenished methane is still unknown. Cryovolcanism, slow outgassing through the crust, and a connection to a subsurface liquid water ocean remain the leading candidate explanations, and current data cannot yet distinguish clearly between them. The magic islands first spotted by Cassini's radar in Ligeia Mare remain unexplained, with waves, nitrogen bubbles, and floating solid material still standing as competing possibilities rather than a confirmed answer. The precise thickness and structure of Titan's haze layer at different altitudes and seasons is still being refined, and the exact rate at which the newly measured photochemistry will affect visibility for an incoming spacecraft in 2034 is not yet fully quantified. These are not failures of the science. They are the normal, honest state of an active area of research, and identifying open questions clearly is one of the more valuable outcomes any observing campaign can produce, because it tells the next mission exactly what still needs to be measured. Dragonfly itself is expected to resolve some of these questions directly once it arrives, since a rotorcraft flying through Titan's lower atmosphere and sampling material at the surface will gather a category of data that no orbiting telescope, however capable, can produce from Earth or from Earth orbit. Ground truth measurements taken directly at the surface and through the layers of atmosphere in between. carry a kind of certainty that remote spectroscopy cannot fully replace. However precise that spectroscopy becomes, Dragonfly is not the only mission positioned to add to this picture. NASA's Europa Clipper, launched in October of 2024, is on its way to Jupiter's moon Europa to study its ice shell and subsurface ocean in far greater detail than previous missions allowed, directly testing many of the questions raised by the earlier revisions to Europa's ice thickness estimates. Concept studies for a dedicated mission to Enceladus, potentially designed to fly directly through its water vapor plumes and analyze their chemistry for signs relevant to habitability, continue to be developed and proposed within the planetary science community, building on what Cassini's more limited flybys were able to measure. Taken together, these efforts represent a level of sustained investment in understanding the outer solar system's icy and hydrocarbon-rich worlds that is arguably higher right now than at any earlier point in the history of space exploration. That investment matters because catching up to the real complexity of these worlds is not a small thing, even though it is not the same as having fully caught up. Webb's Titan observations represent real progress, not a step backward. The instruments now available, spectrographs sensitive enough to detect short-lived molecular fragments like the methyl radical, cameras capable of resolving cloud features and haze structure with far more precision than earlier telescopes, are finally approaching the sensitivity needed to ask the kinds of detailed chemical and dynamical questions that Cassini's instruments, remarkable as they were for their era, could not fully answer. Dragonfly, when it arrives at Titan in 2034, will be flying with the benefit of everything Webb measured in the years leading up to launch, even if the spacecraft's physical design was largely finalized before some of that data arrived. There is a broader lesson embedded in Titan's case that applies well beyond this one moon. Every world humans have studied closely, given enough time and a sufficiently capable instrument, has turned out to be more active and more complicated than the models built before that instrument arrived. That includes Titan itself during the Cassini era, when the magic islands and the unexplained methane persistence were already hinting at gaps in the models before the mission ended. It includes Europa, Enceladus, Pluto, and Io. The consistency of that pattern across such different types of worlds, icy moons, hydrocarbon moons, dwarf planets, and volcanic moons, suggests the gap is not really about any single body being unusually strange. It is about how planetary models are built in the first place, using assumptions calibrated on the two worlds humans understand best, Earth and the Moon, and then extended outward into environments that do not necessarily follow the same rules. None of this is a reason to distrust planetary science or to treat every new finding as evidence that scientists do not know what they are talking about. It is closer to the opposite. The willingness to revise a model when new data contradicts it publicly in peer-reviewed papers that anyone can eventually read is exactly how science is supposed to work. What makes Titan's case worth paying close attention to right now is the timing. A $3 billion mission is in its final stages of assembly, built against atmospheric assumptions that are actively being revised while the spacecraft sits in a clean room. That is not a flaw in how Dragonfly was planned. It is simply what happens when the pace of new astronomical data collides with the multi-year timeline required to design, build, and launch a spacecraft to the outer solar system. Titan's atmosphere is running its photochemistry faster than the models used to plan Dragonfly assumed. Its haze is thicker than the Cassini-era baseline. Clouds are appearing at latitudes and times the seasonal models did not predict. The source of its continuously replenished methane remains unidentified. And the broader pattern across the outer solar system suggests these are not isolated surprises, but part of a consistent trend in how poorly Earth-calibrated models transfer to genuinely different worlds. Individually, each of these findings is a normal, useful scientific result. Together, arriving on the same moon in the years immediately before a major mission's arrival, they describe a world that is stranger, more chemically active, and less fully mapped than the comfortable public picture built during the Cassini era suggested. If you found this kind of close look at what a mission's data actually shows useful, following along or subscribing means these deeper breakdowns of new planetary science keep showing up as the results come in, particularly as Dragonfly gets closer to launch, and Webb continues its ongoing observations of Titan and the rest of the outer solar system. Part of why Titan draws this level of sustained scientific attention comes down to astrobiology, the study of the conditions that could allow life, or at least the chemical precursors to life, to arise. Titan is rich in exactly the kind of complex organic chemistry that laboratory experiments on Earth have long identified as relevant to prebiotic chemistry, the set of chemical reactions thought to precede the origin of life. The atmosphere's photochemistry, the same process responsible for producing the methyl radical web detected, continuously generates a range of increasingly complex hydrocarbon and nitrogen-bearing molecules that rain down onto the surface over geological timescales, building up organic material across Titan's dunes, plains, and lake basins. That organic richness would matter less if it existed in complete isolation from liquid water, since most chemical pathways relevant to the origin of life on Earth depend on reactions happening in a liquid medium. This is where Titan's likely subsurface ocean becomes scientifically significant. Gravitational data collected during Cassini's flybys, based on subtle variations in the spacecraft's trajectory as it passed close to Titan, is consistent with a global layer of liquid water existing beneath Titan's outer ice shell, similar in general concept to the subsurface oceans inferred at Europa and Enceladus, though considerably deeper beneath Titan's surface. If organic material from the atmosphere and surface can, even occasionally, make contact with that subsurface liquid water, whether through impact events that briefly melt ice, cracks in the shell, or slow percolation over long timescales, the resulting chemistry becomes directly relevant to origin of life research in a way that surface organics sitting on frozen, water-free ground would not be. This is precisely the scientific reasoning behind Dragonfly's choice of the Selk impact crater as its primary destination. An impact large enough to form a crater of that size would have generated enough heat to melt a portion of the surface ice, creating a temporary body of liquid water that could have mixed with the surrounding organic material before eventually refreezing. Selk crater is old enough that any liquid water produced by the original impact would be long gone by now, but the chemical signatures left behind in the surrounding material, if Dragonfly's instruments can detect and characterize them, would offer scientists a rare direct look at what happens when Titan's organic chemistry and liquid water actually meet, even briefly. That is the specific scientific payoff the mission is designed to deliver, and it is also exactly the kind of measurement that depends on Dragonfly's cameras and sensors performing well enough, through whatever haze density Titan's atmosphere actually has by 2034, to identify and reach the right locations. Taken as a whole, the picture that emerges from combining Cassini's foundational 13 years of data with Webb's more recent, higher precision observations is of a moon that behaves less like a frozen, static curiosity and more like an actively cycling chemical system, one that is still generating new organic material, still puzzling scientists with an unexplained and continuously replenished methane supply, and still capable of producing measurements that require revising models built only a few years earlier. Dragonfly's arrival in 2034 will not be the end of that process. It will most likely be the beginning of the next round of revisions, informed by direct measurements no telescope, however capable, can fully replace. What Cassini started and Webb continued, Dragonfly is positioned to extend further, provided the atmosphere it flies through behaves closely enough to what the newest data suggests it will. For now, the honest summary is this: Titan is better understood than it was a decade ago. And it is also, in several specific and measurable ways, stranger than the models used to plan the next mission assumed it would be. Both of those statements are true at the same time, and holding them together, rather than picking whichever one makes for a cleaner headline, is the accurate way to describe where the science currently stands.